Full screen? Perfect.
Okay, folks, I hope you've had enough time to kind of try some of these. Factoring fully, this is actually kind of tricky because they don't specifically outline which factoring method is going to be the one that's going to work here. It's kind of up to us to be a little clever and just think about what these things look like and what's the best way to approach them. Now, the first rule of factoring always is common factor first. We're always looking for a common factor. In this first example, part A, it's not a common factor. Now, the next thing I'm looking at is that A value, because if that A, when I say A value, I'm talking about AX squared plus BX plus C. I'm talking about this A value. If that A value is 1, it's going to be a simple factoring binomial. If that A value is not 1, we're going to have to do some decomposition. So we're actually fortunate enough to see the A value is 1. So we're just going to go into sum and product. I like to draw it out like this. Something times something equals 45. Something plus something equals negative 14. Now, I'm sure after a ton of factoring practice, you kind of picked up some tips and tricks. We're multiplying to a positive number, but we have to add to a negative number. So that might tell us something about the two numbers here that'll satisfy this. Does anyone know what the two numbers are? Are there two numbers even? Negative 9 and negative 5. Negative 9, negative 5. Does that work? Positive 45, yeah. Negative 9, negative 5, for sure. Negative 14. So we could do the short factoring method here. We could just go ahead and say, all right, well, this is going to be x minus 9, x minus 5. And the only reason why we're allowed to get away with something like that is because, again, that A value is 1. And that kind of, we should be happy about that. You know, we're like, woohoo, nice one. Sweet. Now we move on to B. The A value is not 1. We're like, oh man. But remember, the first rule of factoring is there a common factor? When we have a look at this 3, negative 3, and negative 36, I'm sure you know that there's a greatest common factor of 3. So we're going to divide the common factor right out of here. Make sure you keep it out front of the brackets. Otherwise, you're changing many things here. So we'll end up with 1x squared minus 1x minus 12. Perfect. Now, we look inside of those brackets, and we're actually, you see that? We're pumped. We like that because it's just a coefficient of 1. So, hey, so we know that we can just simple factor this. We're looking for, so maybe over here, I'll say, okay, something times something equals negative 12. Something plus something equals negative 1. Negative 4, positive 3. Yeah? Negative 4, positive 3 works. Negative 4, positive 3 works. So what we're going to do, we're going to keep that greatest common factor out front, and the trinomial will factor into x minus 4, x plus 3. It is imperative that that greatest common factor stays out front. If it's not there, you've changed the whole quadratic. It's completely different. Like, we know that this is Peter Parker, this is Spider-Man. We know that. We love that. Same thing, different form. But if that 3 is not there, it's like Peter Parker and Mr. Bowden. Like, totally different. Why did he come to my mind? Okay, down here, 2x squared minus 11x plus 12. The first rule, we're looking for the greatest common factor, and we so badly want the greatest common factor to be 2 so that we can common factor this 2 out of there. But because the B value is 11, or negative 11, which is prime, we actually can't really common factor anything here. So here we go. We're going to have to do some, A is not 1. Therefore, we're looking at decomposition. I'm going to write decomp. So 2 times 12 is 24. So we're trying to multiply to 24, and we're trying to add to negative 11. Now, if you're someone that might struggle to find the two numbers that make this thing work, then you should probably write out all the factors. every single one. But if you're someone who's like, no, I think I'm pretty good at this, you could just kind of sit here and think about it for a little while. I'm thinking -8, -3. Yeah? Okay, so let's say -8, -3. -8 times -3 is positive 24. And this one adds to -11, so we're good. So what we're going to do is break up this minus 11x. Now, it truly doesn't matter. We learned that the other day, where it doesn't matter which term goes first, but there surely is an easier one to go first. I think I'm gonna put the -8 first here, because at some point we know we're going to group factor this with a 2, and then the -3 is going to go second, because we know at some point we're going to group factor that with the 12. So I almost put, yeah. You could have done it the other way around, but it's just a little bit easier. I'm forgetting my equal sign here, sorry. Now, we go ahead and we group factor. The greatest common factor out of the first two terms is going to be 2x, and we're left with x minus 4. Okay. And then the second one will be -3, and we're left with, again, x minus 4. Now, whenever there's a negative here at the front, we should usually always common factor it out. You will know if you've done this correctly if you have an x minus 4 and an x minus 4. So we common factor out an x minus 4, and we're left with 2x minus 3. So far, so good? This is a great decomp question. This is a great one. I mean, some of the ones near the end of the homework the other night was a little wild, but that's something more what we're that's something more where we're headed. Okay, part D. This one looks a little funny, doesn't it? When we have a look at all three of those terms, we're looking for the greatest common factor. We notice that they all have an x. They all have at least one x. Do you see that? We have a look again, and they all have at least one y. I mean, the first term has 3 of the y's, the second term has 2 of the y's, the last term has 1 of the y's. So I believe our greatest common factor is going to be xy. 1 xy. Now we're really going to have to pull out our grade 9 exponent law rules here. So the x cancels with x. We're left with 1y squared. Okay. Plus 2x cancels with x, y2 will go away with that, and we're left with 2y. And then here, I believe it's just a 1. Anything divided by itself is just 1. Oh, and would you look at that? Inside of the brackets, what do we got here? We got a simple trinomial. So something times something equals 1, something plus something equals 2, and I think it's 1 and 1, positive 1, positive 1. So we keep the greatest common factor out front, and we get y plus 1 and y plus 1. And then because there's something multiplied by itself, we can kind of condense that into y plus 1 squared. Right? Okay. Tons of factoring. Tons of warm-up here. Does anyone have any questions about any of these? Because these are 4, I think pretty good questions. Do they feel okay? Felt great? Okay. Now, actually, before we get into kind of this stuff here, I want to ask you what we know about square terms. What is, now this is just between us. What is a square number? When someone says a number is square, this isn't on your sheet, I just need you to help me out here. What is a square number? When they say, oh yeah, that number is square, what do they actually mean? Anyone have any idea? Or can maybe someone give me an example of a square number? Have you heard of a square number yet? Yeah, 25 is a great example. So we say example. 25. How do you know 25 is a square number? Yeah. So we could say it's a square number. It's the result of multiplying something by itself. Right? The result of that. So you say 25. Where does 25 come from? Well, if we had a square, and we're calculating the area, and it was 5 by 5, 5 times 5 is 25. Yeah, absolutely. What's another example of a square number? 81. Yeah, how did you get that? Yeah, 9 times 9 is 81. Absolutely. Another one? 64. Yeah, and how do we get 64? Yeah, 8 times 8. Okay, I think we get the idea. Now, those are square numbers, which are lovely. Now, how about this? Can variables be square? Can variables be square? Yeah, I'm getting some nods. Yes? Yes? Who's got an example of a square variable? Don't overthink it. Square variable? Well, how about this one? X squared. We actually say it when we say it. We say it's x squared. Now, we said that something that's square is the result of multiplying something by itself. So what do we multiply by itself to get x squared? Yeah, so if we had a square here, it would be x times x, which is x squared. Okay, how about another one? Anyone have another one? Now, maybe not y squared or z squared or anything squared. What about maybe like y to the exponent 4? Is that square? Yeah, I got a nod. Yeah. What? Well, I think I agree, because that's the result of doing y squared times y squared, right? What about something like z to the exponent 6? Is that square? Yeah, got some nods? And that's maybe because it's the result of doing z to the exponent 3 times z to the exponent 3. You got to remember, we are multiplying here, but we just end up adding these exponents when we multiply powers of the same base. Now, my last question is, can binomials be square? Can binomials be square? Binomial means two terms. So, for example, like, I don't know, a binomial. Can they be square? Got some nods? Well, maybe we should back up a bit. Let's talk about square terms. So maybe you can give me a thumb up, like yes, it's square, or a thumb down, like no, that's not square. 16, is that square? Square? Yeah, okay, great. Yeah, that is square because it's the result of 4 by 4. How about now 16x squared? Is that square? Yeah, I got some nods. Yeah? Now, how do we know that for sure? Well, what my brain does, my brain looks at the 16. I go, okay, is 16 square? Yes, we just said that. Okay. And is x squared square? Well, yes, we know that from up here. So them combined should kind of give us a square term. What about 100x? Is that a square term? I got some shakes saying, no, that is not a square term. I mean, 100 is certainly a square number on its own, but because of that x, it makes it not a square term. If it was 100x squared, that'd be awesome. How about negative 169z to the exponent 4? Is that square? Who says no? No? Why not? Well, to the power of 4 would be something like this. What do you think, Tiana?
No, because multiply to a negative, one number will have to be negative.
Yeah, it's not the result of. Tiana says that in order for us to come up with a negative answer here, one of the numbers that we multiply would have to be positive, the other one would have to be negative. So yeah, very strange. Negative numbers can be a little bit weird here. Okay, I think we get the idea of what's square and what's not. And the last thing I said is binomials. Can binomials be square? I mean, sure, like what if you had like 2x plus 1, right? And you're like, whoa, probably not. But then I did this. Is that square? Yeah, absolutely. Because this would just be the result of doing 2x plus 1 times 2x plus 1. Anything multiplied by itself, we kind of simplify to something like that where we just say that it's squared. Okay. Now, why is that relevant at all? Well, let's go ahead and FOIL some of these out. Now, before we actually go ahead and FOIL these, have a look at each of the brackets. Have a look at the first term, the second term, and then the signs in the brackets. And what do you notice? You see any maybe patterns or something that's going on here? In each of the brackets here, the first term in each bracket is the exact same. Yeah, x and x. The second term is actually also the exact same. 4 and 4. And then the only thing that's kind of different here is that this one is minus and this one is plus. So let's see what happens when we FOIL these types of multiplying binomials. So if we go ahead and FOIL this, we'll get something like x squared plus 4x minus 4x minus 16. And then usually when we FOIL, I know it's been a little while, but we always collect the like terms, and they're usually always the x terms. And what do we end up with here? Well, that'd be 0x, wouldn't it? So we would just end up with x squared and then that minus 16. Because this plus 4x and minus 4x, they kind of just cancel each other out here. Okay, how about this one? First terms are both 2x. Second terms are both 7. One has a minus, one has a plus. Let's go ahead and FOIL this. We should get 4x squared plus 14x minus 14x minus 49. And again, we're going to collect our like terms, which are always the x's here. And we end up with something like this, 4x squared minus 49. Okay, this one's a little bit different. It's got a 3 out front of it, but it still follows the same kind of pattern with the factors here. First term is x, second term is 5, one with a minus, one with a plus. Let's go ahead and do this one. I guess I saved the 3 for the end here. I just FOILed it. X squared plus 5x minus 25. We're going to collect our like terms here, as we always do. 3 times x squared minus 25. Interesting. And then, of course, we distribute that 3 to both terms in the bracket. Get 3x squared minus 75. Now, what do you notice in all 3? I know we haven't done that fourth one yet, but what do you notice about all 3 of these? What's happening? What's something that's common that happens in all 3? What do you notice? The b term. Where is it? Standard form is ax squared plus bx plus c. And what happens is we actually don't have this term at the very end line of each and every single one of these. There's no just like x term. It disappears. And that's not by an accident. This is a very, what we call a special case. Very special case. It says here, notice that the solutions result in a binomial where the 2 terms are being subtracted. This occurs when you multiply 2 identical binomials together, where one is adding and the other one is subtracting. We have a very special name when we factor these types of quadratic expressions, these ones down here. Because we know, we know how to expand and simplify, but when we factor, we go upward. Now there's a very, very, very special way that we factor these ones, which might be a lot easier than you think. We call it a difference of squares. And it's when you have a square term, and they're separated by subtraction. The word difference comes from the subtraction, and the word squares, and it's plural, is because each term there, the A term and the C term, are both square. A polynomial in this form, ax squared minus c, is a difference of squares when you can take the perfect square root of each of them. So for example, and they can be factored just like this here. Now it kind of looks a little strange down there, but maybe I'll show you what I mean here. Our job is to go, as factoring machines, we are to go, starting at the x squared minus 16, we want to go up to factored form. Now if you look closely, x squared minus 16. Well, think about what's the square root of x squared? The square root of x squared. It's kind of silly to even say that because it's just going to be x. And then how about the square root of 16? Is just 4. So because they're both square terms and they're separated by subtraction, we could just go ahead now and put them in this order. First term x, x, second term 4, 4, 1 with a minus, 1 with a plus. It's a very special case, and that's the best way to factor them. Even here, what's the square root of 4x squared? It's just 2x. Right? Square root of 4 is 2. Square root of x squared is x. And then the square root of 49 is 7. So we're going to say 2x minus 7, 2x plus 7. Question? Yes, it will work for C. But C, remember, what's the first rule of factoring? Common factor. 3x. So when we common factor out the 3, notice x squared minus 25 is in the brackets here. So what's the square root of x squared? X. What's the square root of 25? 5. It's kind of nice. It's actually really nice. Now, maybe best to show you through examples. Here's a couple examples. We notice that each of these is a binomial. Remember binomial? Binomial means two terms. In fact, when you see a binomial, any binomial that you have to factor, there should be something that goes off in your brain that says, oh, okay, this could be something special. Notice that x squared is a square term. Notice that 100 is also a square term, and they're separated by subtraction. So this is what we call a difference of squares. We have a difference, which is subtraction of two square terms. So what we can do is think about the square root of x squared, which is just x. Think about the square root of 100, which is 10. Our answer will always be 2 brackets, 1 with a minus, 1 with a plus. That's the way difference of squares just work out. So the first term was x squared here. We square rooted x squared and just got x. So x is going to become the first term, and 10 is going to become the second term. Any questions about this first one here? Feel all right with that? Okay. How about B? Do we have, we see it's a binomial, it's separated by subtraction. So we think, okay, well, what's the square root of 25x squared? Well, I think that's just going to be 5x. And then the square root of 64, we know is 8. So when we set up our answer, forgot my equal sign. When we set up our answer here, we're going to have 2 brackets, 1 with a minus, 1 with a plus. First term is going to be 5x. Second term is going to be 8. Not bad, right? Not bad. How about here? Has anyone got it? One with a minus, one with a plus. We already know this is how it's going to work out because we notice it's a difference of squares. Square root of 4x squared is 2x. Square root of 49 is 7. So we should have 2x in the first position, 7 in the second position. Folks, are there any questions so far after those first three? You're probably wondering, why does this work? Well, this is actually would work out the same way as if we treated it like this. So maybe we'll grab a again. A is x squared minus 100, right? And if we use the difference of squares method, it's honestly pretty simple. You agree? Like it's not so bad. But what we're really used to seeing is this, right? Because we're always missing that bx term. Now, this is a simple trinomial. So what we do to factor this is say something times something equals negative 100, something plus something equals 0, right? Now, what are the numbers that satisfy these two statements? Whoops. Well, they got to add to 0 and multiply to negative 100. So I think it's going to be positive 10 and negative 10, positive 10 and negative 10, and that works. And if you go ahead, we would just factor this the old-fashioned way, x plus 10, x minus 10. And if you have a look, we're just avoiding more work. This is a real nice shortcut for a difference of squares, and you're allowed to use it here. Cool? Now, this one. We look at the number 32, and we're like, oh, that's not, if it was 36, we'd be happy with it. 50, oh man, 50 is not square. If it were like 100 or something, that'd be awesome. So just don't forget, like the first rule of factoring is there a common factor? If you look closely, you'll notice that each of these are divisible by 2. I think 2 might be it. That may just be the greatest common factor here. So we can divide this by 2, divide this by 2, keep the 2 out front of the brackets, and we should have 16x squared minus 25. Okay? And can we factor that a little bit further? Absolutely. It's going to be keep the 2 out front, and we should be, okay, something with a minus, something with a plus. So I think we're going to say here, square root of 16x squared is 4x. 4x will go in the first position. Square root of just the 25 here will be 5. Now, I know I have a ton of brackets there, but it's just so we can see what's going on here. But really, you might have something like that. Folks, any questions about this method? You like it? Hate it? Love it? All right. Okay. I told you this can get a little bonkers. A little crazy. A little. If you look, do we have 2 square, I suppose we call them terms? Do we have 2 square terms? Well, we got 2x minus 4y squared. That's square. 3x plus 7y squared, yes, and they're separated by subtraction. So this is actually, for sure, a difference of squares problem. And similar to that question we took up this morning here, we can almost factor this in the same way. We know it's going to be brackets. Maybe I should make these a lot bigger because I think we're going to be okay. We know that one of the brackets is going to have a minus. I always put the minus first. I don't know why. And one with a plus. We know that, right? We know that's coming. Now, what was the first term? Well, it was basically just the result of the square root of the first term. So if we take 2x minus 4y squared and then square root it, well, the square root will just cancel the square, and we're just left with 2x minus 4y. So that'll be our first term. That's it. 2x minus 4y here. 2x minus 4y there. Now, the second one, it's bracket 3x plus 7y squared. And if we square root this one, the square root will cancel with the square, and we're left with 3x plus 7y. So this will become our second term. 3x plus 7y and 3x plus 7y. Now it looks like we just kind of made a big mess, but until I move on, can I get a check in here? Do you see where this came from? Give me a nod, yeah? Okay, great. So this is where we kind of, you notice inside of each bracket, what we're going to do is just simplify the contents within each of the red brackets here. And when I say simplify, all we're doing is either subtracting or adding polynomials. Now, the weirdest part about this is that, if there's nothing or a plus out front of the bracket, we're allowed to drop the brackets. Do you remember that from grade 9 maybe? Or maybe you thought of it as, imagine a 1 out front of the bracket and you distribute a 1, and basically what we're doing here is just dropping the brackets. So we have 2x minus 4y. We'll just drop the first pair of brackets until we get here. We see this minus. And I remember it was either me or Mr. Todd. We did one of these, and we were upset about the minus there. Do you remember that? And what the minus did was we had to kind of distribute it to each term inside of the brackets because we are subtracting this entire blue bracket. So it's almost as if there's a negative 1 out front. So we'll end up with minus 3x minus 7y. Now the second bracket here is not so bad because out front of the purple one or pink one, there's nothing, so we could just drop the brackets. And out front of the blue one, there's a plus, which indicates we can just drop the brackets. Now, I think our final step here is to kind of look for some like terms within the brackets. I'm looking here. I see 2x minus 3x is negative x, and then negative 4y minus 7y is minus 11y. And over here, 2x plus 3x is 5x, minus 4y plus 7y is plus 3y. And that's about as far as we can go. Like I said, it can get a little wild here. Can. Maybe not will, Okay, folks, we got some questions here. Now, before I actually let you off, this slide right here, I think, is number one. Whenever you're factoring anything, we got to work from right here. The first step of factoring. Step one is common factor. We're looking for a common factor. Now, whether there is or isn't, that's fine. The first step should always be common factoring. Then you have a look at whatever quadratic expression you're factoring. And if it's a binomial, right, that means two terms, we should be looking for a difference of squares, right? If we have a square term and another square term separated by subtraction, that's a difference of squares. But if it's not a difference of squares, then we are done. Yeah? Now, let's just say we went this route. We common factored, whether we did or didn't, whatever. Then it's a trinomial. We're like, all right, trinomial. A trinomial where a is 1. You can find two numbers. This is something like this. X squared plus 5x plus 6. We love these. They're simple. They're short, right? The short way. But then where a is not 1, we kind of got to use this decomposition method here, where this is something like, 2x squared plus 11x plus 9, something like that. I don't know. I'm just making them up. I don't even know if that'll work. But I'm just saying that, A is not 1 and it's not a common factor. This is what we should be thinking when we approach any type of factoring question, I think ever. Okay. Questions about anything? Okay. All right. Folks, the homework is right over here on the previous slide. 230, 231, 3 to 7. And then in 10 ACE, just remember to common factor first.